Thank you so much for being here and choosing to spend some quiet time with this video about what Earth looked like in the Paleozoic era. If you enjoy this kind of calm, science-focused content, please consider giving the video a like, subscribing to the channel, and sharing it with someone who might also find it relaxing. It really helps this small channel grow. I'd also love to know what time of day are you listening to this and where in the world are you right now? Feel free to let me know in the comments. From a long distance away, Earth in the early Paleozoic appears as a rotating blue and white sphere with only small interruptions of muted brown and gray land. The sun is slightly less bright than in later ages, and its light falls across the planet in a steady rhythm set by days that are a little shorter than modern days. The spin of the planet is a touch faster, so the boundary between day and night passes more often over any given point on the surface. From this vantage, the most striking feature is the dominance of ocean. Water wraps around most of the globe as a continuous shell broken only by scattered continental fragments, and the outline of a larger southern landmass that holds much of the solid crust above sea level. Near the poles, the angle of sunlight is low and soft, and any ice that may be present is patchy and uncertain, less extensive than in many later eras, because the greenhouse gases in the air trap enough heat to keep much of the planet free of permanent snow. The atmosphere forms a thin, bright rim around the disk of the planet. Seen against the darkness of space, it is a pale band that grades from deep blue near the surface to a lighter halo toward space. The gases within it are not yet in the same balance as in later times. Oxygen is present but at lower levels, and carbon dioxide is higher. Yet at this scale, the detailed composition does not stand out. Only the overall clarity and thickness of the air are visible as a glowing ring. Cloud systems swirl and twist over the oceans. Large, bright white spirals mark storm systems that form where warm surface waters and cooler upper air interact. Bands of clouds outline broad wind belts that encircle the globe, driven by the rotation of Earth and the difference in heating between equator and poles. The equatorial region carries a persistent broken belt of tall cloud towers and thunderstorms where rising warm air sheds its moisture. Farther from the equator, elongated storm tracks curve across the oceans, guided by pressure differences and the position of the continents. Land areas are irregular and small compared with the area of sea. One major aggregation of crust lies mainly in southern latitudes, a protocontinent that will later become more recognizable as Gondwana. From orbit, it shows as an uneven patch of dull colors edged by wide continental shelves that disappear beneath the shallow seas at its margins. A number of smaller continental blocks and island arcs host their own narrow coastal bands and interior uplands. Their arrangement is not fixed. Over millions of years within the Paleozoic, they shift slowly, sliding across the mantle on plates that move at a pace of only a few centimeters each year. Yet, from the long perspective of geologic time, this motion rearranges the map. If this early Paleozoic Earth is watched over such long intervals, the continents seem to drift, touch, and separate again, changing the balance between open ocean and enclosed inland seas, and altering the exact outline of shorelines. The tilt of Earth's axis relative to its orbit is already established near a value that broadly resembles the modern tilt, so the pattern of seasons is familiar in outline. As Earth travels once around the sun, high latitudes lean toward the light for part of the year and away for the remainder. From space, this produces a slow breathing pattern in the polar regions where the area of snow, sea ice, and seasonal cloud cover grows and shrinks. At some times, in the early Paleozoic polar ice is limited to small caps or even seasonal patches. At other times, especially when continents drift nearer to the poles, ice sheets may expand and the bright reflective areas at high latitudes become more extensive, sending more sunlight back into space and contributing to cooler conditions. Over ocean, the surface colors range from deep blue in clear nutrient-poor gyres to greener or browner tones along certain margins where sediments and microscopic life are more abundant. From orbit, these variations are subtle. They hint at life, but do not reveal its forms. The overall impression is of a planet whose surface is ruled by water, with land as scattered punctuation. The transition between day and night, the terminator sweeps continuously around the globe. On the day side, the sun's light glints off calm regions of ocean and catches the tops of clouds. On the night side, there is no artificial light, only darkness broken by the faint glow of air glow and possibly by flashes of lightning inside storm systems. Because the day is slightly shorter, the cycles of heating and cooling at the surface run a little faster, but from this distant viewpoint, it is only the tempo of the rotating disk that changes. The gravitational interaction between Earth and its moon is already gradually slowing the spin and pushing the moon slightly farther away, but the orbiting satellite still appears somewhat larger in the early Paleozoic sky than it will in later times. From space, the moon's path around Earth is steady, and together the pair move through their orbit around the sun in a nearly unchanging cycle. Over tens of millions of years, small differences in orbit and tilt occur known as orbital variations. But at this outer scale, they register mainly as gentle shifts in the contrast between seasons and in the reach of ice. The early Paleozoic atmosphere, though different in detail, is already effective at scattering blue wavelengths of sunlight, so the dominant tone of the sunlit side remains blue. Along coastlines, wide, shallow seas create lighter-colored bands, where sunlight penetrates to the seafloor and reflects from submerged sediments and carbonates. Inland weather systems that pass over land release rain and change the pattern of soil and rock exposure, but their effect on the outer view is limited to the motion of cloud fields and transient changes in surface albedo. No large continents yet display the deep greens of extensive forests. Those will arise later. Instead, the muted palette of rock, thin soil, and early low vegetation covers the limited land surfaces across the length of the early Paleozoic. From this far perspective, Earth is a dynamic but stable water world. The constant interplay of rotation, orbital motion, and internal heat shapes the large-scale pattern seen from space. Oceans dominate the disk, clouds track the circulation of air, continents drift slowly, and polar ice advances and retreats in response to subtle changes in sunlight and greenhouse gases. All the complex events within the oceans and on land, including the early steps of animal life in the seas and the distant beginnings of plant life on shore, are at this scale only faint influences on color, texture, and reflectivity. The main impression remains that of a mostly oceanic planet turning steadily under a slightly dimmer sun, with its thin atmospheric shell and modest land areas, hinting at processes that will become more visible only when the viewpoint moves inward. In the Paleozoic atmosphere, the sky above the planet is shaped by gases, fine particles, and moving air currents that respond to sunlight and the distribution of oceans and land. The air is still mostly nitrogen, as it is in later ages, but oxygen and carbon dioxide follow different paths through time. At the beginning of the Paleozoic, oxygen is present at lower levels than in later eras, while carbon dioxide is higher, supporting a climate that is generally mild to warm, especially over low latitudes and broad, shallow seas. As the Paleozoic progresses, the balance between these gases shifts. With the spread of marine photosynthetic organisms and later the rise of complex land plants, oxygen tends to increase and carbon dioxide tends to fall, but the path is not smooth. Intervals of volcanic outgassing, burial of organic carbon, weathering of rocks, and changes in ocean circulation all alter the ratio of gases in the air. The result is an atmosphere whose composition changes slowly on human scales, but meaningfully on geologic scales, with consequences for climate clouds and the way light moves through the sky. Over equatorial oceans, warm surface waters heat the air above them. This rising air forms a broad band of convection that circles the planet, drawing moist air upward, where it cools and condenses into tall cloud systems. These clouds are thick and bright, with strong vertical development, and they release heavy rains that fall back into the sea or onto nearby coasts. Seen from the ground, the equatorial sky is often filled with towering clouds that build during the warm part of the day and diminish at night, while higher cirrus layers drift overhead as thin fibrous streaks formed from ice crystals in the cold upper troposphere. Poleward of this convective belt air that has lost moisture flows away from the equator at high altitude and later sinks, creating broad regions of descending drier air. In these belts, the sky is often clearer and sunlight passes through a relatively dust-free column of air, producing a deep, steady blue on clear days. The positions of these belts change slightly as continents move, sea level rises and falls, and the global temperature field reorganizes. But the general pattern of a moist equatorial zone and drier subtropics persists through much of the Paleozoic. Farther toward the poles, where solar energy arrives at a lower angle, air is cooler and often more unstable. Here, large low-pressure systems travel along broad storm tracks. Their clouds form extensive layered decks that can cover large areas of sky, especially where cold and warm air masses meet above the oceans or along the margins of continents. During intervals when polar ice sheets grow, the contrast between cold high latitudes and warmer lower latitudes strengthens, and storm tracks can become more active, with more frequent and intense cyclones moving moisture and heat toward the poles. At other times, when polar regions are milder and ice is limited, the gradient weakens and storm systems are more subdued. Volcanic activity is an important contributor to the look of the Paleozoic sky. Large eruptions inject ash and sulfur-rich gases high into the atmosphere. The ash falls out relatively quickly, dusting land and sea surfaces, but sulfur dioxide can form tiny sulfate particles in the upper atmosphere that persist longer. These particles reflect and scatter sunlight, sometimes cooling the surface for years and altering the color and clarity of the sky. Under such conditions, daylight can become slightly muted, with softer contrasts and a more diffuse quality, especially near sunrise and sunset, when light travels a longer path through the atmosphere. Between such episodes, when volcanic emission is quieter and particles settle out, the air becomes more transparent again and the sky regains its clearer aspect. Dust also plays a role, especially later in the Paleozoic, when large interior deserts develop on the joined continents. In these regions, strong surface winds lift fine mineral particles into the air, carrying them across long distances. Dust-laden air can give the sky a more washed, pale appearance, particularly near the horizon, and can alter the color of the sun when it is low. These fine particles also act as nuclei on which cloud droplets can form, influencing the structure and brightness of cloud layers. Over warm, shallow seas near continents, sea salt and organic aerosols add their own microscopic particles, helping to generate low marine clouds that reflect sunlight back into space. Across the Paleozoic, trends in oxygen and plant cover influence another feature of the atmosphere: wildfires. In the earlier Paleozoic, when oxygen levels are relatively low, fires are limited or absent on land, and the sky rarely carries smoke from burning vegetation. As land plants spread and oxygen levels rise, particularly in the late Paleozoic, fire becomes more feasible. During dry intervals in vegetated regions, lightning can ignite surface fuels, creating plumes of smoke that rise into the lower atmosphere. These plumes darken the sky, locally add soot and organic particles, and cut direct sunlight, though their global influence is episodic. In swampy, humid regions, frequent moisture limits the spread of fire, keeping smoke confined and intermittent. Temperature in the lower atmosphere follows the pattern set by incoming solar energy, greenhouse gas levels, and surface conditions. Over the course of the Paleozoic, there are warmer intervals with high carbon dioxide and minimal ice, and cooler intervals when carbon dioxide is reduced and large ice sheets grow, especially toward the end of the Ordovician and again near the close of the Paleozoic. During warmer times, the vertical temperature profile of the troposphere supports higher cloud tops and vigorous thunderstorms in the tropics. During cooler times, more stable stratified layers may form in some regions with widespread low clouds and fog over cold water and snow-covered land. These patterns change slowly on geological timescales, yet on any given day the sky in a specific place is the result of local weather embedded in broader climate. Light passing through the Paleozoic atmosphere interacts with these changing gases, particles, and clouds. Rayleigh scattering by molecules in the air gives the zenith sky its blue color on clear days, while larger particles from dust, sea salt, or volcanic aerosols scatter light differently, brightening the horizon and sometimes giving it a whitish or yellowish cast. When the sun is high, light is strong and relatively white, though subtle differences in scattering and absorption by water vapor, carbon dioxide, and other gases alter the spectrum slightly. When the sun is low, the path through the atmosphere is longer. More blue light is scattered out of the direct beam, and the remaining light is enriched in longer wavelengths, giving sunrises and sunsets warm tones whose intensity depends on how clean or hazy the air is. The patterns of day length and seasonal light are set by Earth's rotation and orbit and remain within ranges that are broadly similar to later eras. Days are somewhat shorter at the start of the Paleozoic and lengthen very slowly over tens of millions of years, as tidal interaction with the moon transfers angular momentum and slows the spin. But this change is gradual. Seasons arise from the tilt of Earth's axis, producing long summer days and short winter days at high latitudes, while equatorial regions experience nearly equal day and night all year. In icy episodes, High latitudes may see extensive seasonal snow cover under low winter sun with long nights and brief, low-angled daylight. In warmer episodes, high-latitude summers can be relatively mild with longer periods of liquid water and active atmospheric convection. Through all these shifts, the Paleozoic sky remains a dynamic interface between space and surface, shaped by evolving gas composition circulation patterns and the presence of oceans and growing continents below. Clouds, haze, and clear air alternate in complex patterns, but the basic elements stay familiar. A blue dome on clear days, layered or towering clouds that form and dissipate, and a steady cycle of light and darkness that marks the rotation of the planet and the slow progression of seasons over this long interval of Earth's history. Viewed now from closer orbit, the surface of Earth in the early Paleozoic reveals the detailed shape of continents and the wide spread of shallow seas that flood their margins. The main southern landmass occupies a large share of one hemisphere, a composite continent made from earlier crustal blocks that have collided and welded together. Its outline is irregular, with long embayments, peninsulas, and projecting arcs created by ancient mountain belts and rifted margins. Along its edges, the solid rock of the continent slopes gently down beneath clear, relatively warm water. These flooded shelves support broad epicontinental seas, shallow bodies of marine water that spread far inland over low-lying crust. The boundary between open ocean and land is therefore not a sharp line, but a wide gradational zone where coastal plains pass underwater and re-emerge as shoals, islands, and partial barriers. Smaller continental fragments and microcontinents lie scattered across the global ocean. Some are long, narrow slivers that fringe the main landmass like detached ribs. Others stand alone as isolated blocks, their cores built of older crystalline rocks that rise above sea level as modest uplands. Between them, long volcanic arcs curve over subduction zones where oceanic crust descends into the mantle. These arcs add fresh land in the form of chains of islands, some narrow and steep-sided, others backed by small basins that trap sediments eroded from new volcanic slopes. Across the early Paleozoic plate motion slowly rearranges this pattern. The southern composite continent drifts closer to the pole or farther away, depending on the interval, changing its climate and the distribution of ice and desert across its surface. Island arcs and small continents migrate toward or away from it, sometimes colliding to raise mountain belts, sometimes rifting to open narrow ocean basins. On time scales of tens of millions of years, maps drawn for different moments would show wide gateways between ocean basins opening and closing, with corresponding changes in the routes available for ocean currents and in the shapes of shorelines. The shallow inland seas that cover parts of the continents are among the most distinctive features of this time. These seas occupy low areas of crust that have subsided under the combined weights of sediments and tectonic loads, or that lie near sea level because of long wavelength warping of the lithosphere. Their depths are often only tens of meters, and sunlight can reach the seafloor over large areas. In clear water, the color of these seas from above is a lighter blue or turquoise, influenced by the reflection from underlying sand carbonate mud or shell debris. Where rivers deliver abundant mud and silt, the water takes on greener or browner hues. The shorelines of these epicontinental seas do not remain fixed. Global sea level moves up and down, as the volume of mid-ocean ridges changes as sediments accumulate on the seafloor, and in later Paleozoic intervals as ice sheets grow and decay. Small changes in sea level lead to large shifts in shoreline position because the flooded shelves are broad and gently sloping. During high stands, shallow seas spread across wide continental interiors, creating extensive networks of bays, sounds, and embayments. During low stands, the seas retreat toward the continental margins, exposing former seafloors as coastal plains cut by river systems that adjust to the new base level. At the start of the Paleozoic, continental surfaces in many regions are relatively low and smooth, having been worn down by long periods of erosion. On these subdued landscapes, the contrast between highlands and lowlands is modest. Ancient mountain belts left from earlier collisions still stand as ridges, but they are reduced compared with their original peaks, softened into broad upland regions with rounded profiles. Valleys and basins between them collect sediments carried by rivers and coastal currents. These sediments, consisting of sand, silt, and clay, record the position of shorelines and the depth of water through their layering and grain size. Later, in the Paleozoic, new mountain ranges rise as continents converge. When smaller land masses and island arcs collide with larger continents, crust thickens and is pushed upward. Long linear belts of high ground form with steep slopes facing adjacent basins. At their birth, these mountain chains are rugged and steep, with sharp peaks and deep valleys. Over millions of years, erosion lowers them and carries their material outward. The debris from these mountains fills nearby inland seas and foreland basins with thick wedges of sediment. As these basins subside under the accumulating load, they can maintain shallow marine conditions even while receiving large volumes of sand and mud. From an orbital view, such regions appear as elongated sediment-rich seas pressed against the flanks of highlands, while from the surface they present as broad, shallow shelves backed by distant ranges. In the equatorial belt, many continental margins are drowned beneath warm, relatively stable seas. Here, gentle wave action and steady currents shape low-relief coastlines. Muddy deltas project into the water where rivers deliver fine sediment, while sandy barrier islands and spits form where waves and along-shore currents redistribute coarser grains. Tidal ranges vary depending on basin geometry and the position of continents relative to the pull of the moon and sun. Along some coasts, tides create wide intertidal flats that alternately flood and drain, leaving ripples and mud cracks that later may be preserved in the rock record. Along others, wave energy dominates, carving headlands and cutting cliffs into resistant rock while building beaches in protected embayments. Toward higher southern latitudes, especially when the main southern continent lies closer to the pole and climate shifts toward cooler conditions, glaciers may develop on continental uplands. During such glacial episodes, ice sheets advance from interiors toward the sea, scouring the underlying bedrock and depositing unsorted debris. When these ice margins reach coastlines or inland seas, icebergs calve and drift, dropping stones into marine sediments. Between glacial intervals, or when continents lie nearer to the equator, these high-latitude regions support different surface processes, including periglacial weathering, river erosion, and the formation of cold but ice-free shelves. The presence or absence of extensive ice thus changes not only climate and sea level, but also the immediate look of continental edges and polar basins. The floors of the deep ocean basins are relatively uniform in broad shape, but dynamic in detail. Mid-ocean ridges, long chains of submarine volcanoes, run through the basins, creating regions of elevated crust, where new oceanic lithosphere forms. These ridges meander between continents, splitting basins into separate chambers. From the perspective of the surface, they are invisible, but they influence the depth and extent of surrounding waters and the patterns of ocean circulation that will be considered later. Where oceanic plates descend beneath continents, deep trenches mark the surface expression of subduction zones. These trenches are narrow, linear depressions flanking the continental margins or island arcs. They represent the transition from the stable interior of oceanic plates to the zone where they bend and dive downward. Sediments from continents and islands slump and slide into these trenches, where they are partly scraped off and added to the upper plate, building accretionary wedges, and partly carried down into deeper levels of the earth. Over the full length of the Paleozoic, the motion of these plates gradually reorganizes the entire arrangement of continents and oceans. Early in the era, multiple mid-sized continents and smaller blocks are separated by several major ocean basins. As time goes on, collisions progressively assemble larger land masses, and by the late Paleozoic, many of the major continents gather into a single extensive supercontinent that spans a wide range of latitudes. As this aggregation proceeds, interior regions of the joined landmass move far from moderating marine influences. Broad continental interiors develop where distance from the sea and the pattern of air circulation favor more extreme seasonal temperature swings, and under suitable conditions, the formation of extensive arid zones. Simultaneously, the assembly of the supercontinent changes the shapes and connections of surrounding seas. Some earlier ocean basins are closed as continents collide, leaving behind only narrow remnant seas caught between converging blocks. Other basins grow larger as the remaining oceans expand. Long, narrow inland seas can persist in down-warped regions within or along the edges of the supercontinent, connected to the open ocean by restricted straits. These seas pass through phases of normal marine conditions, restricted circulation, and sometimes partial isolation, depending on tectonic subsidence sediment supply and sea level. Their waters can range from clear and well-mixed to stratified and prone to evaporation and salt deposition. At every Paleozoic stage, the look of Earth's surface is therefore a composite of these elements. Drifting continents with their uplands and lowlands, migrating mountain belts, epicontinental seas that wax and wane, coastal plains that alternately flood and emerge, and deep ocean basins with ridges and trenches between them. From the planetary scale down to the regional scale, the distribution of solid land and shallow water sets the stage upon which later sections will describe oceans, coasts, and habitats. Here, at the level of continents and inland seas, Earth in the Paleozoic is a world of slow but constant rearrangement, where familiar processes of plate motion, erosion, and sedimentation gradually reshape the map over the long span of this era. Across the Cambrian and Ordovician, the open oceans form a continuous layered envelope of water that wraps around the planet's solid surface and responds to wind, sunlight, and the arrangement of continents and basins. At the top lies a surface layer that interacts directly with the atmosphere. Here, wind transfers momentum into the water-building waves and driving currents, while sunlight warms the upper tens of meters. The strength of this warming depends on latitude and season. Near the equator, high sun angles and persistent clear days heat the surface most strongly, maintaining a warm, well-mixed layer. Toward higher latitudes, sunlight arrives at a lower angle and for shorter periods in winter, so surface waters are cooler and the mixed layer can deepen as cold, dense water sinks and is replaced by water from below. Under calm conditions, the surface appears as a broad expanse of long, low waves with small ripples on top, their spacing set by wind speed and duration. During storms, especially in mid and high latitudes, stronger winds generate larger waves and whitecaps, and heavy rain streaks the surface. These physical patterns are familiar from later times because the basic controls of gravity, rotation, and wind are the same. Beneath the surface layer, temperature and density change with depth. In warm regions, a thermocline separates the mixed upper layer from colder, more stable, deep water below. Across this boundary, temperature can drop by several degrees Celsius over a relatively short vertical distance, while salinity may change more gradually depending on evaporation and rainfall patterns at the surface. The presence and strength of the thermocline vary with season and location. In equatorial and subtropical belts, strong heating and relatively calm conditions favor a pronounced thermocline and a shallow, warm lens of water. In higher latitudes, where surface cooling and storms are common, mixing can erode the thermocline, especially in winter, allowing surface waters to exchange more directly with deeper layers. The color and clarity of the Cambrian and Ordovician open oceans reflect both physics and biology. Over much of the deep ocean far from land, the water is relatively clear. In these regions, there is little suspended sediment because rivers and coastal processes cannot easily deliver particles to the distant basin interior, and much of the fine material that does reach the open ocean settles slowly to depth. Microscopic life is present, but not as dense as in later eras when certain plankton groups diversify. As a result, the water often appears a deep, pure blue when viewed from above, with light penetrating tens of meters before being attenuated. In zones where upwelling brings nutrient-rich deep water toward the surface, microscopic photosynthetic organisms become more abundant, imparting greener tones to the upper ocean. These bands and patches of enhanced productivity trace the paths of currents and the interaction between wind and basin geometry, producing a mottled pattern of blues and greens across the ocean's surface. The motion of water on a planetary scale follows patterns set by the rotation of Earth, the distribution of heat between equator and poles, and the outlines of continents and ocean basins. In the Cambrian and Ordovician, with a large southern continent and several smaller blocks scattered across wide oceans, wind-driven currents organize into broad gyres in each major basin. In the subtropics, trade winds and westerlies drive surface water into rotating systems that circulate clockwise in one hemisphere and anti-clockwise in the other, depending on the sign of the Coriolis effect. Along the western sides of basins, narrow, fast currents carry warm surface water poleward, while broader, slower flows return cooler water equatorward along the eastern margins. Where these currents run against continental edges or island arcs, they interact with shelf breaks and irregular coastlines, creating eddies and filaments of water that extend offshore or onto the shelf. In some areas, winds blowing parallel to the coast cause surface water to move away from the shore, drawing colder, nutrient-rich water upward in a process known as coastal upwelling. Although the exact positions of these upwelling zones in the Cambrian and Ordovician are not known in fine detail, the combination of winds and basin geometry would have produced such features in at least some locations, with consequences for both chemistry and biology. Below the wind-driven layer, deeper circulation responds more to density differences created by temperature and salinity than to direct wind forcing. Cold, dense water formed at high latitudes tends to sink and spread along the seafloor, displacing older deep water and slowly ventilating the interior of basins. The efficiency of this process depends on the presence of open pathways between polar regions and the deep ocean, and on the shape of continental shelves and slopes. In the early Paleozoic, there are intervals when deep waters are well oxygenated across broad areas, supporting benthic communities on the seafloor. There are also intervals in regions where restricted circulation basin shape and high organic matter input lead to reduced oxygen levels at depth. In such settings, the transition from oxygenated upper water to oxygen-poor or anoxic deep water lies somewhere below the surface, creating vertical chemical gradients that are later recorded in the sediments. During parts of the Ordovician, evidence suggests that some deep basins may experience expanded low oxygen zones, especially during climate shifts or changes in nutrient supply. At high latitudes, the interaction between ocean and cryosphere changes the appearance of the sea. During warmer intervals, polar oceans may be seasonally ice-free with cold, dark waters fringed by snow-covered land. During cooler intervals, glaciers and ice sheets can advance from continents into the sea, forming floating ice shelves and sea ice cover. At the sea ice edge, narrow bands of open water exist where winds and currents keep the surface partially free of ice. Here, sharp gradients in temperature and salinity form, and brine rejected from forming sea ice sinks, contributing to deep water formation. The presence of sea ice alters albedo and insolation, reflecting more sunlight and limiting heat exchange between ocean and atmosphere. It also affects the distribution of life near the surface, because light is reduced beneath thick ice, while open leads and polynyas can host concentrated blooms when conditions allow. In mid-latitudes, storm tracks pass over the open ocean, driving strong winds that whip the surface into breaking waves and inject air bubbles down into the upper layers. These bubbles later rise and burst, returning gases to the atmosphere and producing sea spray that delivers salt and other substances aloft. Rainfall patterns follow the movement of storm systems, with bands of precipitation that freshen surface waters in some regions and leave others relatively saline under the influence of net evaporation. Salinity patterns are further shaped by the location of river mouths, which freshen adjacent coastal seas, and by the balance between evaporation and rainfall over subtropical gyres, which can make surface waters there slightly saltier and more dense. Chemically, the seawater of Cambrian and Ordovician open oceans carries dissolved ions derived from the weathering of continents and from hydrothermal exchange at mid-ocean ridges. Calcium and carbonate ions often reach concentrations that keep much of the water column saturated with respect to common carbonate minerals, allowing shells and other calcareous structures to form and survive in shallow and intermediate depths. Though local variations in saturation state occur with changes in temperature, pressure, and carbon dioxide content. Silica is also present and cycles through the ocean. But the precise distribution of silica using organisms differs from later eras when some planktonic groups become more prominent. Nutrients such as nitrate and phosphate are regenerated in deep waters as organic material sinks and is decomposed, then returned to the surface through mixing and upwelling, setting the capacity of the upper ocean to support photosynthetic life. From the perspective of the water column itself, the Cambrian and Ordovician open ocean is a vertically structured environment in constant slow motion. Near the surface, light penetrates down through the clear water and fades with depth. In the upper tens of meters, photosynthetic microorganisms and other small plankton drift with the currents. Their abundance varies from region to region, following nutrient supply. Below this sunlit zone, light becomes dim and then disappears, giving way to the twilight and dark zones, where vision, if present among organisms, must rely on faint traces of downwelling light or bioluminescence. Temperature and density stratification in these layers act as barriers to mixing, but internal waves and episodic overturning can slowly move water masses up or down. At the bottom of deep basins, soft sediments accumulate as a fine rain of particles from above. Clay minerals, microscopic skeletal fragments, and organic debris settle out of the water column, forming thin layers that drape the seafloor. Over time, these layers thicken, compact, and eventually lithify into sedimentary rocks that will preserve clues to the chemistry and circulation of these ancient oceans. In some areas, low oxygen conditions at depth limit the activity of burrowing organisms and slow the breakdown of organic matter, leading to the preservation of dark organic rich layers. In more oxygenated regions, abundant benthic life reworks the upper sediment, leaving mixed and burrowed fabrics that record a different set of conditions. Throughout the Cambrian and Ordovician, the broad appearance and structure of the open oceans remain governed by the same fundamental processes that act today when shaping the surface density, driving deep circulation, and the position of continents guiding currents. The details differ in response to distinct atmospheric compositions, tectonic configurations, and evolving life, but the overall picture is that of a stratified circulating global ocean system, layered from warm wind, stirred surface waters down to cold, slowly moving abyssal depths, covering most of the planet during this early part of the Paleozoic Era. In the Silurian and Devonian, the global ocean retains the same basic layered structure seen earlier in the Paleozoic, but the details of its temperature circulation and chemistry adjust to shifting continents, changing climates, and the gradual expansion of life. At the surface, broad belts of wind still drive waves and currents, but the outlines of continents and island arcs are now different, and new seaways have opened or closed as earlier oceans narrow and younger basins widen. Where a cluster of continents lies near the equator, large stretches of warm, shallow marginal seas connect with deeper basins, forming long pathways for surface water to move between low and middle latitudes. In these regions, sunlight warms the upper ocean through much of the year, and the result is an extensive, seasonally stable mixed layer that can reach several tens of meters thickness, with a clear thermocline beneath it, marking the transition to cooler, denser water. Over this warm belt, the sky often carries convective cloud bands that bring frequent showers and thunderstorms, and each storm mixes the surface layer, redistributing heat, salt, and dissolved gases. Beneath the waves, the mixed layer is almost uniform in temperature from the surface down to its base, where the gradient steepens and the thermocline begins. This thermocline is typically sharper and more persistent in the Silurian and Devonian subtropical and tropical belts than it is at higher latitudes. The stable stratification here helps maintain warm surface waters above cooler deep waters and also affects the vertical distribution of dissolved oxygen and nutrients. During calm spells, the thermocline can act as a barrier that slows the upward motion of nutrient-rich deep water, while during periods of strong wind or seasonal cooling, the barrier weakens and pulses of deeper water reach the sunlit zone. These pulses are especially important along continental slopes and island arcs, where the interaction of currents with irregular topography can force deep water upward, supplying nutrients to overlying layers and supporting dense populations of plankton and reef-building organisms in adjacent shallows. In mid-latitudes, where the contrast between warm equatorial waters and cooler polar regions is more pronounced, the mixed layer responds strongly to seasonal changes. During warm seasons, solar heating stratifies the upper ocean, creating a relatively shallow mixed layer overlying a pronounced thermocline. During cold seasons, surface cooling and more frequent storms deepen the mixed layer, eroding the thermocline and allowing surface waters to exchange more fully with the underlying ocean. Over the course of a year, the depth of the mixed layer in these zones can expand and contract by many tens of meters, and the seasonal cycle in temperature at the surface is mirrored by shifts in the vertical position of isotherms through the upper few hundred meters. This seasonality in vertical structure is recorded later in layers of sediment that show alternating bands of more and less biologically rich deposits. But in the moment, it is visible only as subtle changes in color clarity and the patterns of floating material. Farther toward the poles, cooler surface waters and at times the presence of seasonal sea ice create different conditions. In high-latitude basins, where dense surface waters form during winter, cooling, salty, cold water sinks to depth, initiating deep overturning that helps ventilate interior layers. This process is aided where continents and island arcs leave open pathways from the polar regions into the deep ocean basins. The sinking water spreads along the seafloor as a slow, cold bottom current, displacing older deep waters and gradually renewing oxygen at depth. The exact regions where this deep water formation is most active are constrained by the arrangements of land masses and the positions of constricted gateways, but in general parts of the Silurian and Devonian oceans show enhanced deep circulation, where cold surface waters can access the deep interior. In contrast, where basins are partly enclosed by surrounding land, or where sills and ridges isolate them from the main deep ocean water exchange at depth can be restricted. In such settings, organic matter that sinks from the surface is not fully broken down in the presence of abundant oxygen. Instead, respiration gradually reduces oxygen concentrations in intermediate and deep waters, leading to wide zones of low oxygen or even anoxic conditions. During intervals of especially high organic input or limited deep ventilation, such zones can expand upward, forming broad oxygen minimum layers in the water column and leaving a characteristic imprint of dark, fine-grained sediments on the seafloor. The chemistry of Silurian and Devonian seawater reflects ongoing weathering on land hydrothermal exchange at mid-ocean ridges and biological cycling in the water column. Calcium, magnesium, sodium, and other major ions remain present at levels high enough to keep seawater chemistry broadly similar across the basins. But the relative proportions can shift, slowly influencing which carbonate minerals are favored. At times, seawater is more favorable to the precipitation and preservation of certain forms of calcium carbonate on the seafloor and in shallow shelves, and at other times, the balance tilts slightly. Carbonate saturation states, especially in the surface and upper ocean, usually remain high enough for shell-building organisms and reef structures to develop, but local and regional fluctuations occur with changes in carbon dioxide levels, temperature, and alkalinity. In the Silurian, much of the land surface is still relatively low and near sea level in many regions, so numerous shallow seas exchange directly with the open ocean. Rivers deliver dissolved ions and fine sediments from weathered rocks to these margins, influencing coastal salinity and turbidity, but only weakly altering the chemistry of the open ocean. In the Devonian, as some continents cluster and new mountain belts rise, weathering rates can increase in certain catchments, delivering more calcium bicarbonate and other ions to the sea. At the same time, the spread of vascular plants and early forests on land increases the rate of chemical weathering in some regions and enhances the burial of organic carbon in soils and sediments. This burial tends to draw down atmospheric carbon dioxide over long time scales and can influence ocean carbonate chemistry. While such changes are gradual, they create long-term trends in seawater composition and buffering capacity, which in turn affect how the ocean responds to volcanic outgassing and other carbon inputs. Surface salinity patterns in Silurian and Devonian oceans are shaped by the balance of evaporation, rainfall, river input, and ice processes, just as in earlier intervals. In subtropical gyres under descending airnet, evaporation can exceed precipitation, increasing surface salinity and slightly raising density. These saltier surface waters can drift poleward along western boundary currents, carrying heat and salt into higher latitudes. Where they cool, they become dense enough to sink, contributing to intermediate or deep water masses. In contrast, regions under persistent rainfall or near large river mouths can have fresher surface layers that are buoyant and resist mixing downward, maintaining shallow stratification. In high-latitude basins that experience seasonal sea ice, the formation and melting of ice redistribute salt. As sea ice grows, it excludes most of the salt, enriching the underlying water and increasing its density. When the ice melts, it releases fresh water, creating a low salinity surface lens. These processes help shape the vertical layering near the poles and influence when and where deep convection can occur. Biologically, the Silurian and Devonian oceans host more complex and abundant life than earlier in the Paleozoic, and this life interacts with the physical and chemical structure of the water column. Photosynthetic organisms in the upper sunlit zone consume dissolved carbon dioxide and nutrients, producing organic matter and oxygen. Some of this organic matter is eaten and recycled near the surface, while some sinks, carrying carbon and nutrients downward. In oxygen-rich regions, sinking particles are decomposed by organisms and dissolved back into the water column, releasing nutrients into deep and intermediate waters. These nutrients then return to the surface through upwelling and mixing, closing the loop. In regions where deep waters are poorly oxygenated, decomposition proceeds differently, and the balance of chemical species can shift, affecting the cycling of elements such as nitrogen, sulfur, and iron. The strength of this biological pump, which moves carbon from the surface to the interior ocean, is influenced by the abundance and composition of plankton communities, by grazing and predation in the upper layers, and by physical processes that set the depth of mixing and the rate of upwelling. Although the precise shapes and sizes of mid-Paleozoic basins differ from modern oceans, currents still wrap around them in large gyres, narrow boundary flows, and deep return paths. At the surface bands of warmer and cooler water trace the flow of these currents across the seascape, and gradients in temperature and salinity define fronts where water masses meet. Along these fronts, vertical mixing can be enhanced, bringing nutrients into the lighted zone and supporting elevated biological activity. At depth, more sluggish currents carry water masses that bear the chemical fingerprints of the regions where they formed, including distinct temperature salinity and nutrient signatures. Over thousands of years, these water masses slowly traverse the basins, eventually rising or mixing back toward the surface, where their stored nutrients and carbon are once again exposed to the atmosphere. Seen in its full structure, the Silurian and Devonian Ocean is thus a three-dimensional fluid system that integrates surface-forcing deep circulation and biological activity. Warm stratified layers in the tropics, strongly seasonal mid-latitude belts, and cold episodically overturning polar regions together form a connected network of flows that transport heat salt gases and particles around the globe. The patterns of these flows are shaped by basins whose shapes change only slowly with plate motion, by climate states that shift between relatively warm and cooler intervals, and by evolving life that gradually alters the chemistry of both water and air. From the surface, only the uppermost expression of this system is visible as color gradients, temperature contrasts, and wave patterns, but in depth, unseen layers carry the imprint of Silurian and Devonian conditions through the entire column of water that covers most of Earth during this middle part of the Paleozoic era. Along the margins of early Paleozoic continents, shallow seas spread out as broad carbonate shelves, where light water movement and chemistry combine to build low-relief reefs and skeletal seafloors. In the Cambrian, many of these shelves lie along the flanks of the main southern continent and the edges of smaller continental blocks nearer the equator. The water over them is mostly clear and warm, shallow enough that sunlight reaches the bottom across large areas. On calm days, the surface is patterned by small waves that pass overhead as alternating bands of brightness and shade, while beneath the seafloor is a mosaic of pale carbonate mud, patchy skeletal debris, and scattered mounds of simple reef structures. The earliest reef frameworks in these seas are built not by corals, but by sponge-like animals and microbial communities. Cup-shaped or branching forms, sometimes called archaeochiaths, stand close together in clusters, their porous walls filtering seawater as fine carbonate mud and other particles settle around their bases. Between and on top of these sponge frameworks, thin microbial films and small mound-forming organisms trap and bind sediment-stabilizing patches of the seafloor. Over time, repeated growth and burial create low knobbly buildups that rise slightly above the surrounding shelf, forming natural irregularities in an otherwise gently sloping surface. Around these mounds, trilobites, brachiopods, and other early shelly animals occupy the spaces between sponges and microbial crusts. Their empty shells, along with fragments of skeletal material from other organisms, accumulate as layers of gravel and sand-sized particles that drape the reef flanks and nearby flats. In the shallowest settings, waves and currents winnow fine mud from these accumulations, leaving well-sorted, rippled beds of shell hash and carbonate sand. Farther from wave base, where water motion is slower, finer mud settles out, creating smooth, soft substrates that contrast with the rougher textures of skeletal shoals. During storms, stronger waves and currents sweep across the shelf, picking up loose sediment and moving it shoreward or basinward. On the seafloor, this activity is recorded as scoured surfaces, hummocky, cross-bedded layers, and lenses of coarser grains that fill depressions. Between major events, quieter conditions allow animals to recolonize the disturbed areas, burrowing into freshly deposited layers and leaving networks of tunnels and feeding traces just beneath the surface. These burrows mix sediment and help maintain a relatively uniform superficial layer, but the overall fabric remains that of a shelf dominated by carbonate production and reworking, rather than by thick accumulations of riverborne mud. As time moves into the Ordovician, carbonate shelves in many regions support more elaborate reef systems. Tabulate and rugose corals appear and increasingly contribute to reef frameworks, often in association with stout, massive sponges and other skeletal organisms. In clear, low-latitude seas, these combinations build reefs that are more continuous and topographically pronounced than the earlier mounds. The cores of such reefs show dense thickets of branching and plate-like corals cemented together by carbonate precipitated in the spaces between skeletons, and by encrusting organisms that coat exposed surfaces. On the flanks, debris from broken corals and sponges tumbles downslope, forming aprons of coarse, skeletal talus that grade outward into mixed skeletal and muddy sediments. The water above these early coral-rich reefs is often highly transparent, with sunlight reaching several tens of meters below the surface. In shallow zones, the play of light across coral surfaces and sponge walls is modulated by the gentle motion of waves, producing shifting patterns of brightness on the seafloor. Between coral heads and sponge masses, quieter pockets of sediment host brachiopods anchored by pedicles, crinoids attached to firm substrates, and other suspension feeders that rely on currents to deliver food. The overall visual effect is of a seafloor broken into patches of rigid three-dimensional framework, surrounded by softer, more mobile sedimentary areas. Along strike, these reefs are not continuous walls, but a series of banks and patches separated by channels and lower ground. Some banks form along former shorelines or shelf edges where wave and current energy are highest, while others develop on slightly raised portions of the interior shelf. The geometry of each reef complex is shaped by the interplay between biological growth, sediment supply, water depth, and storm frequency. Where growth keeps pace with subsidence and sea level rise, reef crests remain within the zone of optimal light and wave energy, maintaining their role as barriers that partially protect landward lagoons. Where growth cannot keep up, reefs can drown, leaving behind a relic topography covered by later, more uniform sediments. Landward of reef belts on these carbonate shelves, water becomes slightly more restricted and in places more variable in salinity and clarity. Lagoons behind reefs can host finer carbonate muds, shoal patches of oolitic sand formed by the repeated coating and rolling of tiny grains in agitated supersaturated waters, and scattered patch reefs or skeletal mounds. Tides and winds drive shallow currents across these flats, concentrating sediment in bars and channels that change gradually over time. In some locations, especially where limited siliciclastic input arrives from nearby land, the entire inner shelf may be a broad expanse of carbonate mud and sand with only subtle changes in depth and texture. In others, where rivers deliver clay and silt, mixed carbonate and siliciclastic shelves form with muddier inner zones, grading seaward into clearer carbonate-dominated water. Seaward of reefal and inner shelf zones, carbonate production declines, and the shelf transitions to the upper slope. Here, steeper inclines channel gravity-driven flows of sediment into deeper water. Storms, internal waves, and slow, persistent currents move finer material along the slope, while periodic slumps and turbid flows carry pulses of sand and skeletal debris downslope to form fans and aprons at the base of the slope. These features are not reef habitats themselves, but are connected to the reef and shelf systems above, and they preserve a record of the erosion and redistribution of material originally formed in shallower settings. Across many Cambrian and Ordovician shelves, tidal processes are also important. In narrow seaways and along certain margins, strong tides generate fast currents that ebb and flow over bank tops and through channels, sculpting tidal sand waves and producing rhythmic layering in the sediments. Intertidal zones emerge and submerge on daily cycles, leaving broad flats that alternate between shallow subtidal pools and exposed surfaces with mud cracks and desiccation features. These flats often lie shoreward of reef complexes or along the inner parts of the shelf, where water depth is minimal and slopes are extremely gentle. The repeated wetting and drying in these areas influences both sediment texture and early diagenesis, helping to create hard grounds and early cemented layers that stand out as resistant surfaces during later erosion. The chemical environment across these early carbonate shelves reflects both the open ocean and local conditions. In most shallow regions, seawater remains supersaturated with respect to calcium carbonate, allowing shells and skeletal structures to precipitate and persist. However, small variations in temperature, carbon dioxide levels, and salinity can tip the balance locally toward dissolution or enhanced cementation. Pore waters within sediments differ from overlying seawater as microbial communities break down organic matter and alter acidity and redox conditions. In some restricted lagoons or embayments, evaporation can concentrate salts and change ion ratios, leading to the precipitation of minerals such as gypsum or halite in very shallow or isolated settings. Though these evaporitic fosses are more typical of later, more arid intervals and more confined basins. Within the early Paleozoic, they appear where geography and climate allow sufficient restriction and evaporation. From the perspective of form and texture, the early Paleozoic reefs and carbonate shelves are therefore varied but unified by the dominance of carbonate sedimentation in clear, relatively warm, shallow water. Low to moderate relief reefs, built first by sponge-like organisms and microbial mounds, and later by more complex coral sponge assemblages, rise slightly above the broader, gently sloping platforms that extend inland toward emergent land and outward toward deeper basins. Waves, tides, storms, and currents constantly reshape the loose sediments around these fixed frameworks, while chemical processes and biological activity bind some grains into solid rock even as others remain mobile. Over millions of years within this bounded early interval, The patchwork of reefs, shoals, lagoons, and flats migrates slowly across the shelves as sea level and subsidence rates change. But at any given moment, a cross-section through these environments shows a continuous transition from near-shore carbonate flats across reef belts and outer shelves to slopes and basinal deposits beyond, forming one of the characteristic shallow marine settings of the early Paleozoic world. In the later Paleozoic, coastlines and continental shelves show a more intricate mix of reefs, deltas, tidal flats, and coastal plains as mountain building, changing sea levels, and expanding plant cover on land alter both the supply of sediment and the chemistry of shallow seas. Along some low-latitude margins, clear warm water still supports coral-rich carbonate shelves. Rugose and tabulate corals, together with large sponges and other skeletal organisms, build reef complexes that form irregular belts parallel to shore or along the outer shelf edge. These late Paleozoic reefs often reach greater relief than their early Paleozoic predecessors, with compact cores, where dense thickets of coral skeletons and massive sponge bodies create rigid frameworks. Between and on top of these structures, crinoids, brachiopods, and other suspension feeders anchor themselves, adding their own skeletons to the pile. When storms cross the shelf, waves break over the reef crests, churning water and snapping fragile branches. Broken pieces fall downslope as coarse debris, forming talus fans that merge with surrounding skeletal sands. Landward of the reef belts, protected lagoons host quieter water. Here, carbonate mud settles in broad flats, and islands built from skeletal sand and oolitic grains rise slightly above mean sea level. Tidal channels wind through this low terrain, carrying water in and out on daily cycles. On flood tides, clear water from seaward spills across shoals and bars. On ebb tides, slightly muddier water, with a higher load of fine suspended sediment, drains back toward the open sea. The lagoon floor is a patchwork of firm ground, soft muds, and small patch reefs. In places with strong tidal flows, elongated sand waves and mega ripples align with current directions, shifting gradually over time as each tidal cycle rearranges grains. In other late Paleozoic regions, particularly where new mountain ranges rise inland, the character of the coast is very different. Uplifted ranges erode under the action of weather rivers and gravity, sending large volumes of sand, silt, and clay toward the sea. Along such margins, deltas advance into shallow epicontinental seas. Viewed from above, these deltas show lobat or triangular shapes with one or several main distributary channels reaching the coast and branching into a network of smaller channels that divide and rejoin as they cross low vegetated plains. At the shoreline, these distributaries split into multiple mouths that discharge fresh water and sediment into the basin-building mouthbars and subaqueous levees. Coarse sand tends to settle near the river mouths and in channel bottoms, while finer silt and clay spread farther out, forming laterally extensive thin layers over predelta slopes and neighboring shelves. The seaward side of these deltas is lined by shallow bays and embayments filled with brackish water, where salinity varies with tides, river discharge, and storms. During floods, plumes of turbid fresh water spread across the adjacent shelf as lighter surface lenses carrying suspended sediment that slowly settles, creating graded layers. During dry intervals, clear marine water can penetrate farther inland along estuaries. Tidal ranges in these settings depend on basin geometry and the position of the delta within larger embayments, but in many cases tidal currents are strong enough to form broad intertidal flats. These flats are composed of silty mud, fine sand, or a mixture of both, and they display a variety of small-scale structures such as ripples, mud cracks, and shallow channels. Twice a day, water floods and drains them, leaving a thin sheen of standing water at low tide in depressions and ponds. These zones are transitional between land and sea, and they preserve fine details of water movement and sediment deposition. In the Carboniferous, when large parts of some continents lie near the equator and the climate over broad regions is warm and humid, many coastal plains support extensive swamp forests. In these regions, the coastal profile includes not only marine shelves and deltas, but also low-lying areas densely covered by trees and undergrowth. Rivers meander across these forested plains before reaching the sea, and their banks and floodplains are lined with thick accumulations of plant material. Where such rivers enter shallow epicontinental seas, they often form muddy, vegetated deltas. The transition from forested swamp to tidal flat and shallow shelf is gradual, with belts of brackish wetlands marking the interface. Over time, repeated flooding, plant growth, and burial in these coastal swamps lead to thick peat layers that, under later pressure and heating, transform into coal seams. The presence of this organic rich material influences the chemical environment of nearby estuaries and coastal waters, affecting oxygen levels in bottom waters and pore fluids within underlying sediments. During parts of the late Paleozoic, especially as the supercontinent assembles and some regions experience more arid climates, different coastal morphologies appear. Along certain margins of the growing supercontinent, arid to semi-arid belts develop where rainfall is limited and evaporation is strong. In these settings, low-gradient coastal plains and enclosed embayments can host broad tidal flats and sabkha-like environments. Here, seawater floods the surface during high tides or storm surges, then partially evaporates under strong sunlight and dry winds. As water evaporates, salts become more concentrated in the remaining film, and minerals such as gypsum and halite can precipitate within surface crusts or in shallow subsurface pore spaces. The resulting flats are smooth to gently irregular, with polygonal mud cracks, evaporate nodules, and thin laminated crusts. Further seaward, normal marine conditions prevail over the outer shelf, but landward, the transition from marine to terrestrial environments is marked by increasingly saline soils and sparse vegetation, rather than by dense swamp forests. Along many late Paleozoic coasts, barrier island systems and strand plains develop where waves and longshore currents are strong and sand supply is sufficient. Chains of elongate low islands built from beach and dune sand lie parallel to the mainland, separated by lagoons and tidal inlets. On the seaward side of each island, a gently sloping beach faces the open sea. Waves break on offshore bars and sweep sand up and down the shore. On the landward side, tidal channels connect the lagoon to the open ocean, distributing marine water and suspended sediment into the back barrier basin. This configuration can migrate landward or seaward as sea level and sediment supply change, but at any time it defines a distinct zone of shallow wave-influenced habitats between the river-fed intercoastal plain and the deeper shelf. Storms play an important role across all of these late Paleozoic coastal systems. When large storms travel along or across a coastline, they generate higher waves and storm surges that temporarily raise water levels. On carbonate shelves, storm waves can push coarse skeletal debris onto reef crests and across back reef flats, forming storm ridges and sheets of broken shells. On siliciclastic deltas and barrier coast, storm surges can overtop barrier islands and levees, depositing sandy layers across marshes and lagoons. These event beds stand out from the finer, more regularly laminated background sediments. Between major storms, fair weather processes rework the deposit, smoothing some features and preserving others. Through repeated episodes, the coastal profile adjusts, with some areas prograding seaward and others retreating landward. The distribution of salinity along these later Paleozoic coasts is complex and highly variable. In regions dominated by large rivers and high rainfall surface waters near the coast are relatively fresh and buoyant. They can form surface plumes that extend many kilometers offshore before mixing with heavier marine water. Beneath these plumes, saltier shelf water persists. In contrast, along arid coasts with few rivers, strong evaporation can raise nearshore salinity, and dense saline water may sink and flow seaward along the bottom. In restricted embayments with limited circulation, these processes can lead to stratification with a fresher surface layer overlying more saline bottom water, or under some conditions, the development of hypersaline basins, where circulation is insufficient to remove dense water quickly. Over geological time, the arrangement and character of these late Paleozoic coastal and shelf habitats shift as sea level climate and tectonic setting change. But the range of environment types remains broadly similar. Clear water reefs and carbonate platforms persist in some low-latitude seas, although the composition and health of reef communities fluctuate, and some intervals see declines in reef growth and gaps in large reef systems. Muddy river, dominated deltas, and associated shore faces expand where mountain belts and highlands deliver sediment, and where subsiding basins create accommodation space for thick sediment wedges. Tidal flats and coastal wetlands spread along gently sloping margins under a range of climatic conditions, either as parts of humid vegetated plains or as drier evaporate-forming flats. Barrier islands and sandy shore faces link these systems, moving sediment along the coast under the combined action of waves and currents. At any one time in the later Paleozoic, a traverse from the outer shelf toward land in a given region might cross from deeper open marine waters onto a storm-influenced shelf across either carbonate reefs or siliciclastic shore faces, and then onto tidal flats, deltas, or swampy plains. The details differ from place to place and time to time, but the overall picture is of coastlines that are increasingly complex, with more pronounced interactions between sediment from land carbonate production in shallow seas and the growing influence of land plants and climate gradients on the shape and substance of the narrow zone where ocean meets continent. On land in the early and middle Paleozoic, the first persistent green appears as a thin discontinuous cover on rock surfaces and along low coastal plains rather than as tall forests. At the start of this interval, exposed continents are largely bare of complex vegetation. Their surfaces are shaped mainly by physical weathering chemical reactions between minerals and the atmosphere, and the action of flowing water and wind. Bedrock ridges and plateaus show fresh fracture plains and coarse debris at their bases. Slopes are mantled by loose blocks and gravel, while lower ground hosts thin layers of sand and silt wash down from higher positions. In many places, The color palette is dominated by grays, browns, and muted reds associated with unweathered rock iron-rich crusts and early soils. Across this mineral landscape, the first visible signs of plant life develop near shorelines, river margins, and damp, low spots where conditions permit. Here, mats of simple photosynthetic organisms cling to moist substrates. Cyanobacterial films and early algae coat rock surfaces in thin, dark layers that become slick when wet and desiccated when dry. On gently sloping tidal flats and estuarine margins, microbial communities stabilize fine sediments, binding grains together into cohesive crusts. These crusts resist erosion during gentle flooding, but can crack and curl as they dry, forming polygonal patterns that mark the repeated alternation between immersion and exposure. Over time, spores and simple propagules from more complex plants reach these same environments. In the Ordovician and early Silurian low bryophyte-like plants begin to colonize select parts of the damp ground. These plants lack true root stems and leaves in the modern sense. Instead, they have simple anchoring structures and flattened bodies that allow them to absorb water and nutrients directly from their surroundings. They remain small, hugging the surface in patches and cushions that follow the microtopography of the substrate. Along stream margins and in shallow depressions that collect water seasonally, these early plants form irregular patches of dark green to olive cover, interspersed with bare sediment and rock. The presence of even such limited plant cover begins to change how the land surface behaves. Where mats and small plants grow, they help trap wind-blown dust and fine sediment carried by overland flow. This trapped material accumulates as a thin veneer of organic, rich soil over the underlying rock or coarse debris. Within this veneer, microbial activity increases, organic molecules build up, and mineral grains weather more rapidly than in completely bare areas. The overall effect is still subtle at the scale of the continent, but becomes evident along favored corridors, such as moist coastal plains and the lower reaches of river systems. Small streams in these zones show banks that are slightly more cohesive and less prone to immediate collapse because plant structures and microbial crusts bind sediments. During floods, water still spreads across these surfaces, but instead of removing all loose material, it leaves behind fine layers that integrate with existing soils. On gently sloping shorelines, these early land plants occupy the upper parts of tidal and supertidal zones, where they experience frequent wetting by spray and occasional inundation, but avoid prolonged submergence. Below them, microbial mats dominate true intertidal flats, while above bare rock and sand still prevail. The transition from fully aquatic to fully terrestrial habitats is thus marked by a gradation of surfaces from submerged muds to intermittently flooded flats to thinly vegetated higher ground. In slightly more inland settings where groundwater approaches the surface and shallow ponds form, these simple plants occupy the damp margins and hummocks that remain moist for much of the year. Around such ponds, the green cover is still patchy, but more continuous than on drier slopes. As the Silurian progresses, new types of plants appear that possess more complex conducting tissues. These early vascular plants, including forms comparable to Cooksonia and related genera, have slender upright axes that rise a short distance above the ground and terminate in simple sporangia. They are usually only a few centimeters to perhaps several tens of centimeters tall and tend to cluster in low stands. In locations where conditions permit, these stands create the first suggestions of vertical structure on land beyond scattered mineral fragments and occasional microbial films. Their color ranges from lighter green in newer tissues to darker tones in older parts, and their presence casts small patches of shade on the substrate. Despite their small stature, such plants represent a significant step in the visual character of near-coastal landscapes. They can transport water from the substrate to elevated tissues, allowing them to grow somewhat taller than bryophyte-like forms. As a result, the land surface they occupy begins to resemble a very low open scrub of thin stalks interspersed with bare ground, rather than a completely plant-free plain. Between the stems, wind-blown silt and organic debris accumulate, and rainwater trickles through this material, further enhancing weathering and soil formation. Fungi also occupy the early Paleozoic land surface, both as free-living decomposers and in association with plants. Filamentous fungal networks grow within the uppermost substrate, breaking down organic matter and interacting with mineral grains. In some descriptions, large upright fungal bodies may be present in localized areas later in this interval, but the overall effect on the appearance of most landscapes is dominated by low plant-covered surfaces and cryptic fungal activity, rather than by frequent tall structures. Together, plants, fungi, and microbial communities form a thin living skin on parts of the continents. Arthropods begin to exploit these environments as they become more stable. Millipede-like forms, early arachnids, and other small terrestrial arthropods move across the land surface, often remaining close to damp microhabitats, where humidity is high and where vegetation or microbial crusts provide both food sources and shelter. Their bodies are rarely conspicuous at a distance, but their presence is recorded in small tracks and burrows on and within the substrate. On wet flats, their footprints and trails intersect ripple marks and mud cracks, creating a dense texture of fine scale surface features. In slightly better drained areas, shallow burrows and resting traces mark where organisms have briefly occupied the sediment. Although these animals are not the focus of this description, their activity contributes to the mixing of the upper sediment and the fragmentation and redistribution of plant material. Climatic conditions during this period vary with latitude and the arrangement of continents, but many of the areas where early land plants thrive share a few traits. They are often located in low-lying regions near coasts or in interior basins where moisture is available for much of the year. In equatorial belts, frequent rainfall maintains damp surfaces, while in higher latitudes, seasonal cycles bring wet intervals punctuated by drier phases. Even in drier regions, shaded crevices, sheltered valley bottoms, and spring-fed areas provide microhabitats where small plant patches can persist. As plate motion brings different parts of continents under varying climate regimes, the distribution of these early terrestrial ecosystems shifts. Some previously vegetated regions may become drier, limiting plant cover, while new areas gain suitable conditions and are colonized. Over longer spans within this bounded time window, the cumulative effect is a gradual lateral expansion of green cover along certain corridors, rather than an abrupt transformation of entire continents at once. Visually, a traveler looking across a typical early Paleozoic coastal plain or lowland in this interval would see a landscape that remains mostly open and low-dominated by bedrock outcrops, thin regolith, and braided or meandering stream channels. However, in certain bands along the lowest ground and near water, The surface is darkened by continuous films of microbial growth and interrupted by irregular patches or belts of small plants. The contrast between bare and vegetated areas is stark, with the green confined to zones of reliable moisture. In cross-section, the thickness of biologically active material is still very small compared with later soils, perhaps only a few centimeters to a few decimeters. But this layer is where most of the chemical exchange between atmosphere, biosphere, and upper crust now occurs. The presence of this thin but expanding biological cover has important consequences for erosion and sediment delivery to the sea. On bare slopes, heavy rains generate sheet flow that rapidly entrains and transports loose particles, cutting rills and gullies. Where plants and microbial mats are present, water infiltrates more easily and flows more slowly, reducing its capacity to carry sediment. As a result, some catchments with more extensive vegetation send finer, more evenly distributed sediment loads to coastal zones, while those with sparser vegetation continue to deliver coarser, more episodic pulses. Over time, this differential behavior influences the shape of valleys, the character of river channels, and the nature of deltas and tidal flats downstream. It also begins to modify the composition and sorting of sediments that will eventually lithify into rocks, preserving signals of early terrestrial ecosystems in the geological record. Through this early stage of land colonization, Earth's continents therefore pass from being almost entirely mineral surfaces with only patchy microbial films to hosting distinct, though still low terrestrial plant communities in select environments. The overall appearance of the continents remains far from the densely vegetated forested landscapes of later Paleozoic intervals. Instead, they show a pattern of bare uplands and sparsely covered slopes feeding into narrow belts of green along river margins, depressions, and coastal plains. Within these belts, the interplay of plants, fungi, microbes, water, and sediment begins to create a more chemically active and structurally diverse surface layer, marking the first major step in the transformation of Earth's land surfaces during the Paleozoic era. In the Devonian, the appearance of Earth's land surface changes more noticeably as rivers begin to run between banks lined with taller plants, and as the first true trees establish broad shaded tracts along lowlands and uplands. Continents that once showed only thin ribbons of low vegetation near coasts now bear more continuous belts of green in certain climate belts, especially near the equator, where warmth and moisture are reliable. From a distance, these regions still lack the dense, closed canopy of later forests everywhere, but in many basins and along many river systems. The ground is no longer a patchwork of bare sediment and small plants. Instead, there are corridors of substantial vegetation that follow drainage networks, climb gentle slopes, and occupy floodplains, giving parts of the land surface a darker, more textured look. In these areas, rivers weave through vegetated valleys and plains, and their courses respond in new ways to the presence of rooted plants and better developed soils. The rivers themselves can take different forms depending on gradient sediment load and discharge. In steeper uplands, streams remain relatively straight and confined, cutting narrow valleys into bedrock or coarse alluvium. Along their margins, clumps of vascular plants hold onto shallow soils, stabilizing small ledges and benches. Downstream, where gradients decrease and sediment accumulates, channels often split into multiple intertwined paths that shift position over time, creating braided patterns across wide gravel and sandbars. In places where vegetation is still sparse, these braided reaches resemble older Paleozoic systems, with broad exposed bars and rapidly migrating threads of flow. However, where plant cover has become more continuous along banks and on bar tops, channels tend to become more stable and locally more sinuous. Roots bind the upper layers of sediment, making banks more resistant to erosion, while fallen plant material accumulates along the margins, trapping finer grains. Over time, these processes encourage the development of meandering river segments, where a single main channel winds back and forth across its floodplain. The cross-section of a typical vegetated Devonian river valley shows several key surfaces. At the lowest level lies the active channel, with its bed of gravel sand and migrating dunes. Slightly above this are low terraces and natural levees built by overbank floods that deposit fine sediment when rivers rise and spill onto their margins. Above these broader floodplain surfaces and abandoned channels, host soils of varying thickness and maturity, interrupted by low ridges where older deposits resist erosion. Vegetation occupies all of these elements, but its density and composition vary with elevation above the channel and with distance from the main flow. Closest to the water, low plants, horsetail-like forms, and early tree ferns cluster along moist banks. Their stems and fronds create a near-continuous fringe that spills over onto exposed sediment during seasonal low flow. Slightly higher on the floodplain, larger, woody plants appear. Early trees, such as Archaeopteris and other progymnosperm forms, produce substantial trunks and branching crowns. Archaeopteris and similar trees have deep, spreading root systems that penetrate weathered rock and soil, extracting water and nutrients while binding the substrate. In stands where these trees dominate, the ground is shaded for much of the day, and the microclimate beneath the canopy is cooler and more humid than the open areas beyond. The litter of fallen leaves, branches, and roots accumulates on the forest floor, forming a layer of organic, rich material that gradually decomposes. Mosses, fungi, and small plants grow among this litter, and in damp hollows, shallow pools, and saturated soils persist long after rainfall events. The vertical profile of these early forests includes several tiers. At the top, the crowns of trees intercept sunlight and wind. Below, an understory of smaller vascular plants and early seedless shrubs occupies the filtered light. Closer to the ground, bryophyte-like mats and seedlings cover parts of the soil surface. The total height of the tallest trees can reach several tens of meters, making these forests a dominant visual element wherever they occur. Their trunks are often straight and columnar with bark that records the growth of the plant over time. Even when individual leaves or fronds are small, the aggregated foliage in the crowns forms a nearly continuous layer that interacts with sunlight, wind, and rain. Between forested belts, more open landscapes persist. On higher, drier uplands, where soils are thinner and water less available, vegetation may be confined to scattered trees, shrubs, and low plants separated by areas of bare rock or thin regolith. In these settings, surface runoff during storms remains vigorous and small channels cut into the substrate, but even there, the presence of roots and plant cover slows erosion relative to completely barren conditions. On interior plateaus and slopes that receive moderate rainfall, a mosaic of woodland and open scrub develops with thicker stands in valleys and more open vegetation on ridges. The resulting pattern, when viewed from an elevated vantage within this interval, is a patchwork of darker, dense forest tracts aligned with drainage lighter open woodlands on intermediate ground and pale rocky or sparsely vegetated areas on the highest or driest terrain. Climate gradients across the Devonian continents shape where these early forests and wooded river systems occur. Near the equator and on windward sides of uplands, warm temperatures and frequent rainfall create humid belts that favor continuous forest along rivers and across lowlands. In these regions, cloud cover is common, and afternoon storms regularly sweep across the landscape, feeding rivers that run year-round. Farther from the equator, seasonal contrasts become more pronounced. Some mid-latitude regions experience warm, wet seasons separated by cooler, drier intervals. Here, forests may still thrive along rivers and in basins, but give way to more open vegetation on uplands during dry phases. At higher latitudes where temperatures are cooler and growing seasons shorter, plant cover may be lower in height and more discontinuous, though wetlands and lake margins can still support dense stands of plants during favorable periods. The increased complexity of land vegetation and soils alters not only the look of the surface, but also the behavior of water at many scales. Rainfall that once flowed rapidly across bare rock now infiltrates more deeply into soil profiles and is taken up by roots. Evapotranspiration, the combined loss of water through evaporation and plant transpiration, returns moisture to the atmosphere, affecting local humidity and possibly the formation of clouds. Flood peaks in vegetated catchments are often lower and more delayed than in poorly vegetated ones because water is temporarily stored in soils, wetlands, and forest litter before it reaches streams. Over geological time, these hydrological changes influence river channel patterns and the stacking of sedimentary deposits in basins. Soils themselves become more developed in many Devonian regions. A soil is a layered weathered material at Earth's surface that supports plant growth. With deeper root systems, enhanced microbial activity, and increased organic input from litter, Devonian soils display more distinct horizons than earlier simple regoliths. Upper layers are enriched in organic matter and have finer structure, while underlying layers show evidence of chemical alteration, such as leaching of certain ions and accumulation of others. In cross-section, bands of color variations mark differences in iron content, drainage, and oxidation state. These soils are thickest where vegetation has been longest established and where climate conditions support sustained weathering, such as in humid lowlands and on stable upland surfaces. In contrast, on rapidly eroding slopes or in regions of active tectonic uplift, soils remain thin and patchy, and bedrock remains close to the surface. Lakes and wetlands are common features of Devonian landscapes associated with these vegetated river systems and early forests. In subsiding basins or along slowly flowing river reaches, water ponds behind natural levees, landslides, or local rises in the bed. The margins of these lakes are lined with stands of emergent plants, while floating and submerged vegetation occupies shallower zones. Organic material accumulates on lake bottoms, often in low oxygen conditions where decomposition is slowed. In some cases, repeated burial of plant material in such settings contributes to the formation of organic rich shales, and where conditions are suitable and sustained over long periods, to the early stages of coal formation, although the most extensive coal accumulations are characteristic of slightly later periods. In the near coastal zone, River mouths and estuaries carry the imprint of both marine and terrestrial influences. Where Devonian forests and plant-covered drainage basins meet shallow seas, deltas and estuarine plains are often densely vegetated. Channels are bordered by trees and smaller plants, and flood events distribute plant debris across the delta top. Driftwood logs and mats of vegetation become common features along shorelines trapped in embayments and stranded on bars. As these organic accumulations decay, they alter the local chemistry of water and sediment, lowering oxygen levels in some bottom waters and contributing to the formation of dark organic rich layers in quiet depositional settings. The presence of rooted plants in delta plains also tends to stabilize distributary channels, promoting the persistence of certain pathways and reducing the frequency of large-scale channel shifts compared with earlier plant-free deltas. Overall, Devonian land surface habitats present a more structured and varied scene than earlier Paleozoic landscapes. Rivers now wind through valleys that are lined with trees and other vascular plants, their banks and floodplains covered by soils that retain water and nutrients. Forests cast shade over extensive areas, especially in equatorial and mid-latitude belts, with humid climates creating cooler, moister microenvironments at the surface. Between these forests, mosaics of woodland scrub and sparsely vegetated uplands persist, maintaining a diversity of ground covers and erosion regimes. From basin to basin, the specific arrangement of these elements changes with topography, climate, and tectonic setting. But the repeated pattern of vegetated river corridors, forested lowlands, and patchy uplands marks the Devonian as a time when Earth's land surface acquires a more recognizably complex and layered appearance within the Paleozoic era. In the Carboniferous part of the Paleozoic, large regions of some continents lie close to the equator and are covered by low-lying basins that receive abundant rainfall throughout much of the year. In these basins, the look of the land surface is very different from earlier times. Wide swamp forests stretch for hundreds of kilometers along shallow inland seas, river plains, and subsiding troughs. The air over these regions is warm and humid, and mist often hangs among the trunks during the cooler parts of the day. Skies above may be bright or overcast depending on passing weather systems, but near the ground, the dense vegetation and high moisture give the land a muted, shaded quality. At the core of these landscapes stand dense forests made up of tall spore-bearing trees and tree-sized plants. Many are lycopsids and horsetail relatives with straight columnar trunks that rise more than 20 meters before branching or supporting narrow crowns of foliage. Others are seed fern-like plants and early gymnosperms with broader, more complex branching patterns. Their trunks are thick and often patterned with scars from fallen leaves and branches. Between the large trees grow smaller shrubs, ferns, and low ground plants that fill most of the available light gaps. The result is a multi-layered plant cover in which very little bare soil is visible. The forest floor is carpeted with fallen leaves, stems, and woody debris in various stages of decay. This litter is often waterlogged because the water table in many of these basins lies close to the surface. Shallow pools and saturated soils are common, and after heavy rains, much of the forest floor becomes a continuous wet surface with standing water and depressions. In slightly higher microtopographic positions, low mounds remain only seasonally flooded, but even there, soils stay moist for long periods. Root systems of the larger trees weave through these soils, anchoring trunks and stabilizing sediments. Many roots radiate outward near the surface before descending, creating a complex, three-dimensional network that helps bind peat and mineral material together. Rivers entering these lowlands from surrounding uplands slow as they encounter the nearly flat swamp surfaces. Channels split and rejoin across the plains, forming networks of distributaries that wander through the forest. Some segments are relatively straight and confined by cohesive root-bound banks. Others meander in broad loops across peat-rich floodplains. Natural levees built by repeated flooding rise slightly above surrounding swamps, and on these levees, trees may grow more densely because roots can tolerate brief intervals of lower water table. During high flow events, rivers overtop their banks and spread thin sheets of water across wide areas, depositing fine silt and clay on top of existing organic rich ground. Over time, this alternation of plant growth, flooding, and burial builds thick sequences of peat layers interbedded with thin mineral horizons. In cross-section, these deposits record repeated cycles of forested swamp development and drowning. Lakes are common features in this carboniferous landscape. Some occupy depressions created by subsidence or by the shifting of river channels. Others lie behind natural barriers where sediment has blocked previous drainage paths. Their shorelines are irregular and graded with zones of open water surrounded by belts of emergent vegetation. Tree trunks and large plants often stand at the water's edge or even rooted within the shallower parts of the lake, their bases submerged while their crowns remain in the air. Beyond them, floating and submerged plants inhabit quieter coves and backwaters. The surfaces of some lakes are partly covered by mats of plant material, and their waters are typically dark-stained by dissolved organic compounds leached from the surrounding peatlands and forests. In many cases, the bottom waters of these lakes are low in oxygen because decomposition of abundant organic matter consumes available oxygen faster than it can be replenished. This low oxygen environment allows fine plant debris to accumulate as thin laminated layers on the lake floor. The combination of forested swamps and associated lakes gives the lowlands a characteristic pattern when viewed from above. Dark belts of tree cover trace river corridors and surround ponds and marshes, separated here and there by lighter patches of more open ground or by slightly raised areas where conditions are too dry for continuous swamp, but still support woodland or scrub. In more coastal basins, the swamp forests may grade outward into tidal marshes and estuaries, where fresh water mixes with incoming marine water. In these areas, salinity fluctuates and vegetation patterns adjust, with some tree species retreating from the most saline zones and salt-tolerant plants occupying the transition. Tidal channels cut sinuous paths through the lowlands, their banks lined with dense vegetation that traps sediment and organic debris. As tides rise and fall, water flows in and out of these channels, redistributing fine material and influencing the thickness and continuity of peat layers. The atmosphere during this time holds higher levels of oxygen than before, influenced in part by the large extent of these swamp forests and the burial of their organic matter. This elevated oxygen content does not change the appearance of the air in a direct visual sense, but it supports large arthropods and robust vertebrate animals that become part of the background texture of the swamp. Insects with broad wingspans move through the humid air above ponds and channels, while large millipede like arthropods travel slowly through the leaf litter, pushing aside small fragments of plants and leaving shallow trackways. Amphibian-like vertebrates rest in shallow water or on damp banks, their bodies partly hidden by vegetation. Their presence is obvious in the patterns of footprints and drag marks that accumulate in soft mud along shorelines and in the margins of drying pools. These traces, along with the fallen logs, roots, and leaf mats, give the forest floor a crowded, uneven texture that contrasts with earlier, simpler landscapes. In the higher parts of the Carboniferous basins where drainage is slightly better or where subsidence is slower, swamp forests grade into better drained forests and woodlands. Here, soils are thicker and more structured with clearer horizons, separating organic rich surface layers from underlying mineral zones. Tree diversity may be somewhat different, and the frequency of standing water is lower, but the overall impression is still of a heavily vegetated landscape with only small open clearings. Fires can occur in these better drained belts under dry conditions, producing charcoal and temporarily clearing patches of forest, but in the perennially wet central swamps, fire remains less common. On the margins of the swamp belts where basins meet uplands or coastal plains, the contrast between environments is sharp. One side may show dense, tall forest with a saturated, organic, rich substrate. The other may present more open ground with braided river sandbars and fewer tall plants. As sea level and tectonic subsidence change the positions of coastlines and accommodation space through time, the zones of swamp, lake, and better drained forest shift laterally, sometimes advancing over previously open ground, and at other times retreating as conditions become less favorable for peat accumulation. Over millions of years within the Carboniferous, the repeated growth and burial of these swamp forests produce thick stacks of peat that under later burial and metamorphism transform into coal. In the present interval, however, what is visible is not the final rock, but the active surface expression of these processes: tall trees, extensive wetlands, dark still waters, and a land surface that is in many basins almost continuously saturated with water and covered by living and decaying plant material. Together, these features mark the Carboniferous lowlands as some of the most densely vegetated and water-rich surface habitats of the Paleozoic Era, creating a distinctive swamp and lake-dominated appearance that differs strongly from earlier Paleozoic landscapes while still fitting within the broader evolution of Earth's land surface during this time. In the Permian, the overall outline of Earth's land surface shifts again as most of the major continents join into one large supercontinent with broad interiors, long coastal margins, and pronounced latitudinal climate gradients. This joined landmass has interior regions that lie far from the moderating influence of the sea, so the contrast between humid coastal belts and dry interior basins becomes one of the most striking features of late Paleozoic landscapes. Along many low to mid-latitude margins, shallow epicontinental seas still lap against the edges of the continent, but their reach into the interior is more limited than in earlier times. Coastal plains, deltas, and narrow swamp belts fringe these seas, yet moving inland relief gradually increases rainfall, declines, and vegetation becomes sparser. River systems that drain from interior uplands toward the sea traverse long distances across semi-arid plains, alternating between confined valleys and broad, low-gradient basins where water spreads out and evaporates. In the deepest parts of some basins, subsidence and limited drainage allow lakes and inland seas to form, but many of these water bodies are ephemeral or fluctuating. Their shorelines advance and retreat as climate cycles and tectonic movements alter the balance between inflow and evaporation. When climates are relatively wet, lakes fill and muddy, or sandy shorelines extend outward. During drier intervals, water levels fall, exposing wide flats of fine sediment that dry crack, and in some cases accumulate evaporate minerals where salinity becomes high. These exposed basin floors are often pale in color, with patches of white and light gray marking salt crusts and gypsum-rich layers, and with networks of desiccation cracks partitioning the surface into irregular polygons. Above these lowlands rise upland regions and mountain belts formed during the collisions that assembled the supercontinent. In some ranges, peaks are rounded by erosion, yet still stand high enough to intercept moist air and generate orographic rainfall on their windward flanks. These wetter slopes support more continuous vegetation cover, including forests in suitable climate zones. On their leeward sides, however, air descends, warms, and dries, casting broad rain shadows across adjacent interior basins. In these rain shadow regions, and in other parts of the continental interior where global circulation patterns limit moisture supply, extensive arid and semi-arid landscapes develop. Here, the surface is dominated by rocky plateaus, gravel plains, dune fields, and ephemeral stream channels. In the most arid belts, dunes built of fine to medium sand cover large areas and migrate slowly over geological timescales. Between dune fields lie flat or gently undulating desert floors, where coarse gravels lag deposits of resistant pebbles and indurated crusts, mark zones of intense wind deflation. During rare rain events, water flows along shallow channels, temporarily filling small depressions and transporting sediment, but for most of the time these surfaces are dry and sparsely vegetated. The distribution of plants in these arid regions is patchy and controlled by access to moisture. In some interior basins, clusters of drought-tolerant trees, shrubs, and low plants gather along ephemeral streams around springs and in depressions where groundwater approaches the surface. Their root systems stabilize local sediment and form small oases of green within a wider matrix of bare or thinly vegetated ground. Elsewhere, scattered woody plants and hardy herbaceous species occupy cracks in bedrock-sheltered positions behind boulders and low rises where fine sediment has accumulated. At higher latitudes and on parts of the supercontinent that lie closer to the poles, climates are colder, and ice plays a more direct role in shaping the land surface. During cooler intervals, ice sheets and alpine glaciers extend across some polar and subpolar regions, carving valleys, smoothing bedrock surfaces, and depositing unsorted debris as they advance and retreat. In such regions, uplands display striated rock surfaces, moraines, and glacially scoured basins that may later hold lakes. Between the cold polar belts and the dry interior tropics, broad temperate zones span parts of the supercontinent. In these zones, seasonal changes in temperature and precipitation are pronounced. Summers can be warm to hot with rainfall concentrated in certain months, while winters are cooler and sometimes marked by frost or snow at higher elevations. Forests and woodlands occupy areas with sufficient water, particularly along rivers on mountain slopes and in basins with reliable precipitation. Trees in these temperate belts may include seed ferns, conifers, and other gymnosperm groups adapted to seasonal climates. Their canopies are not as uniformly dense as those of earlier equatorial swamp forests, but they still form continuous tracts in favorable settings, broken by more open ground on ridges, in drier rain shadow zones, and in regions with shallow rocky soils. Moving across the Permian supercontinent reveals sharp contrasts over relatively short distances. One region may present wide, flat expanses of red and brown sandstones, siltstones, and mudstones forming low mesas and escarpments with sparse vegetation and clear evidence of episodic stream flow in the form of broad channels filled with cross-bedded sands. Nearby higher ground may support more continuous plant cover with tree-lined valleys, seasonal rivers, and patchy undergrowth. Farther toward the coast, lowlands may again show wetter conditions with floodplain swamps and coastal marshes, though these are less extensive than the great equatorial swamps of the Carboniferous. Offshore narrow shelves and coastal seas receive sediment from rivers draining the interior, building deltas and shorelines that respond to both sea level changes and sediment supply. Through the Permian, the positions of arid belts, temperate zones, and polar regions shift as continents move slightly and as atmospheric composition changes. Volcanic activity in some regions contributes ash layers to terrestrial and marine deposits and releases gases that influence climate on various timescales. The burial and exposure of organic rich deposits also affect carbon dioxide levels in the air. These long-term feedbacks, combined with the arrangement of land and sea, led to intervals of relative warmth and intervals of cooler climate with expanded ice in high latitudes. The land surface responds through changes in vegetation, cover the extent of deserts and semi-arid basins, and the balance between erosion and deposition in rivers and basins. Within this late Paleozoic interval, the characteristic appearance of Earth's land is that of a large joined continent with prominent interior dryness, extensive upland and basin systems and climatic zones, arranged broadly by latitude and modulated by topography. Coastal humid belts, temperate woodlands, polar glacial landscapes, and vast arid interiors together define a mosaic of habitats whose distribution and visual character differ from the earlier swamp-dominated lowlands, yet remain within the evolving story of Earth's surface during the Paleozoic era. In the Paleozoic oceans, the seafloor is not a single uniform surface, but a set of environments where particles settle, accumulate, and gradually change into rock. Across deep basins, continental slopes and shallow shelves, sediments record both the physical conditions of the water above and the chemistry of the ocean at the time of deposition. In the deepest parts of ocean basins far from land, the bottom is usually covered by fine-grained material that arrives as a slow rain from the water column. Tiny mineral particles derived from the erosion of continents mix with microscopic remains of marine organisms and with volcanic ash. The rate at which material reaches the seafloor in these settings is low, so it can take thousands of years to build a layer only a few centimeters thick. As a result, sediments here are often thinly bedded, with subtle changes in texture and composition that reflect shifts in climate-ocean circulation and biological activity above. On continental slopes and in deeper parts of epicontinental seas, sediment delivery is more variable. When storms, earthquakes, or the gradual oversteepening of shelf edges destabilize deposits, masses of sand silt and mud can move downslope under gravity. These gravity-driven flows spread out into lobes and fans on the basin floor and leave deposits in which coarser grains at the base grade upward into finer material. Between such events, finer background sediment continues to accumulate from suspension. Over time, the alternation of event layers and quiet water deposits builds a stacked sequence in which individual beds record discrete episodes, while the overall pile reflects longer-term patterns of sediment supply and basin subsidence. On shallow continental shelves, particularly those flooded by epicontinental seas, the seafloor texture is strongly influenced by water depth, wave energy proximity to land, and the balance between carbonate production and siliciclastic input. Near river mouths and along muddy coasts, beds of silt and clay extend seaward as blankets over the shelf. Closer to shore, these sediments may be laminated and bioturbated with burrows and feeding traces from invertebrates. Farther offshore, where wave and current energy rework the surface, the seabed may be organized into ripples and larger sand waves. In carbonate-dominated regions, the shelf floor is covered by mixtures of carbonate mud shell fragments and skeletal sands derived from reefs and other shallow habitats. Storms periodically rearrange these materials, forming cross-stratified beds and lag layers of coarser grains. Between storms, fine mud settles in quieter areas, filling depressions and creating a more even surface. The chemistry of seafloor sediments is closely tied to the state of the overlying water and to processes within the sediment itself. In well-oxygenated settings, such as many shallow shelves with active circulation, oxygen penetrates a short distance into the sediment, supporting burrowing animals and aerobic microbes. These organisms mix the upper layers and oxidize organic matter. Iron in the sediment tends to be present as iron oxides, giving some layers a reddish or brownish color. In deeper settings where oxygen in bottom waters is lower, especially in partially enclosed basins or along margins with strong productivity at the surface, conditions at the sediment-water interface can shift toward oxygen-poor or anoxic states. In such environments, organic matter is not fully decomposed by aerobic processes. Instead, microbial communities use other electron acceptors, such as sulfate, to break down organic material producing reduced species like hydrogen sulfide. These chemical changes alter the composition and color of sediments, often leading to dark gray or black layers rich in organic carbon and iron sulfide minerals. The thickness and extent of these anoxic or disoxic deposits vary over the Paleozoic, expanding during intervals of widespread low oxygen conditions in the oceans and contracting when circulation and oxygen supply improve. Carbonate chemistry also plays a central role in the nature of seafloor deposits. Where seawater is saturated with respect to calcium carbonate and biological production, is high skeletal material accumulates rapidly. On shallow shelves and platforms, this material forms limestones composed of shell fragments, skeletal grains, and carbonate mud. In slightly deeper settings, fine carbonate may settle from suspension or from the breakdown of planktonic shells. The depth at which calcium carbonate dissolves more readily than it accumulates is influenced by temperature pressure and the concentration of dissolved carbon dioxide. During different Paleozoic intervals, the position of this depth can shift, affecting whether deep basin floors are covered by carbonate-rich sediments or by clay-dominated deposits. In regions where deep waters are undersaturated in carbonate shells that sink below certain depths, tend to dissolve before reaching the seafloor, leaving their signal mainly in the chemical composition of deep waters. Volcanic eruptions also leave their mark as thin ash beds that settle onto the seafloor, later altered to clay-rich layers that can be traced across basins and used as time markers. The burial of sediments beneath younger layers leads to progressive changes in their physical and chemical state. As the stack thickens, pressure expels pore water and compacts grains, and dissolved ions in the remaining fluids precipitate as cements binding grains together and transforming loose sediment into rock. Early diagenetic processes, including the growth of nodules and concretionary structures, record the pathways of fluids and the redox conditions within the sediment column. Across the Paleozoic, the distribution and character of seafloor sediments respond to major events such as sea level fluctuations, mountain building, and changes in ocean circulation and climate. Transgressive phases when seas advance over continents promote widespread deposition of shallow marine sediments across shelves and lowlands. Regressive phases expose previous seafloors to erosion and weathering, removing or reworking earlier deposits. Tectonic activity raises some sedimentary packages to form parts of future mountain belts, where once horizontal layers are tilted, folded, and uplifted above sea level. From that point, they become part of the visible continental crust rather than the active seafloor. Yet, in their internal structure and composition, they preserve a record of seafloor conditions that once existed, including signatures of oxygenation productivity, volcanic events, and changes in seawater chemistry during different parts of the Paleozoic era. At any given moment within this interval, a map of the ocean floor would show a patchwork of sediment types and thicknesses, from thin pelagic clays in remote deep basins to thick wedges of turbidites along continental margins and blankets of carbonate or siliciclastic sediments on shelves. Together, these deposits form the material foundation upon which later geological processes act, and their layered chemistry records how Paleozoic oceans interact with the atmosphere, the continents, and the evolving biosphere above. In the Paleozoic soils, coals and weathered rock together form the thin but important layer where the solid earth interacts most directly with air, water, and life. Early in the era before land plants become widespread, this layer is discontinuous and simple. Many exposed surfaces show only a loose cover of broken rock fragments and mineral grains that have been freed by frost thermal stress and chemical reactions with the atmosphere. On slopes and uplands, this regolith is often coarse with blocks, pebbles, and sand resting directly on less altered bedrock. In lower positions and along coasts, fine silt and clay accumulate more easily, but the absence of deep root systems and thick organic horizons keeps most profiles shallow. Where microbial films and the earliest small plants and fungi cover the substrate, a thin darkened zone appears at the top of the weathered rock. This zone contains slightly more organic matter and finer grains than the material below and holds moisture more effectively after rainfall. Even so, the contrast between this surface layer and the underlying rock is modest, and in many regions, the transition from unweathered to weathered material remains sharp within a short vertical distance. As vascular plants spread and forests arise in the Devonian, the look and internal structure of soils change. On stable uplands and long-lived floodplains, thicker weathering profiles develop. At the surface lies an organic rich horizon composed of plant litter mixed with mineral particles. Beneath this, repeated cycles of wetting, drying, percolation, and root activity create zones where minerals are leached of some ions and enriched in others. Iron and manganese can move downward and reprecipitate as nodules or bands, and clay minerals form from the breakdown of feldspars and other primary grains. Vertical sections through such soils show color changes from dark browns near the surface to reds, yellows, and paler tones at depth, reflecting differences in organic content and oxidation state. Roots of trees and other plants penetrate through these horizons, sometimes reaching into fractured bedrock, where they widen cracks and promote further weathering. On slopes, these soils may be thin and discontinuous because erosion removes material nearly as fast as it forms, but on gentler ground, they can reach thicknesses of a meter or more. In regions where climates are humid and warm, especially near the equator, intense chemical weathering of bedrock produces deep, strongly leached profiles. There, much of the original mineral assemblage is broken down, leaving a residue rich in stable oxides and clay. Surfaces in such areas can show extensive reddening. In cooler or drier regions, physical weathering dominates, and soils remain thinner, with more rock fragments and less pronounced chemical alteration. Over the long span of the Paleozoic, these different soil types shift in area as climate zones move with continental drift and as vegetation patterns change. Coal forms in particular parts of this evolving surface layer where plant production is high, decomposition is limited, and sediments repeatedly bury organic matter. The most distinctive examples arise in the Carboniferous, when widespread swamp forests occupy low-lying basins and coastal plains. In these settings, the ground is saturated for much of the year, and fallen plant material accumulates faster than it decays. Trunks, branches, leaves, and fine roots build thick mats on the swamp floor. Because oxygen levels in the waterlogged substrate or low, microbes break down organic matter only partially. Instead of being fully oxidized, much of the carbon remains locked in peat, a spongy, organic, rich material that can reach several meters in thickness. Periodically, changes in relative sea level subsidence or river behavior bring in pulses of mineral sediment. Thin layers of silt clay or sand spread across the peat surface during floods or marine incursions, sealing and compacting the accumulated plant material. New vegetation then colonizes the top of the sediment, and the cycle of growth, accumulation, and burial resumes. Over repeated episodes, a vertical succession emerges in which peat horizons alternate with siliciclastic or carbonate layers. With continued burial under additional sediments, the weight compresses the peat and drives out water. Chemical changes reorganize and concentrate the carbon-transforming peat into lignite and then into harder coals. Although the full conversion may extend into later eras during the late Paleozoic, the surface expression is that of thick, wet peatlands interbedded with more mineral-rich units, and shallow burial already begins the compaction process. The appearance of areas destined to become coal seams is that of dense swamp forest or marsh underlain by dark water-saturated organic deposits, rather than by simple mineral soils. In some coastal basins, these peat accumulations grade laterally into tidally influenced flats and shallow bays, where plant material mixes with marine sediments. Weathered rock in the Permian interior adds another facet to this picture. As arid and semi-arid climates expand across parts of the supercontinent, chemical weathering slows and physical processes sculpt the land. Exposed bedrock surfaces develop thin weathering rinds and case-hardened crusts, where salts and oxides precipitate near the surface. Repeated heating and cooling along with sparse but sometimes intense rainfall, fractures the rock and produces talus and colluvium along slopes. In closed basins, evaporation leaves behind layers of soluble minerals that accumulate at or near the surface as evaporate deposits. Soils in these regions are often saline or alkaline with white or pale incrustations and a blocky structure. Vegetation is sparse and organic horizons are thin or absent. Across glaciated high-latitude regions, late in the Paleozoic weathered materials and soils reflect the advance and retreat of ice. Where ice sheets move over the land, they scrape away pre-existing soils and deposit unsorted glacial till. When the ice melts, this till forms a cover of mixed clay, silt, sand, and stones that blankets bedrock. In some deglaciated areas, fresh soils begin to form on this till, with thin, organic, rich horizons developing under tundra, like vegetation or early forests. Through all of these settings, the materials and chemistry of the upper crust control how water moves, how plants establish, and how much carbon and nutrients are stored at the surface. Deeply weathered profiles in humid belts, thick peat and early coal in subsiding basins, saline-crusted soils in arid interiors, and thin, immature soils in newly glaciated or uplifted areas together form a shifting pattern over the Paleozoic. The visible result is a land surface whose color texture and cohesion vary from place to place, reflecting the combined action of climate tectonics and life on the outermost few meters of rock during this era. Within Paleozoic seas, much of the living and dead material that shapes watercolor chemistry and sediment is too small to see without magnification. The upper sunlit layer of the ocean holds countless microscopic organisms that drift with currents, form thin, hazy clouds in the water column, and ultimately contribute their remains to the seafloor. Early in the Paleozoic, simple photosynthetic microbes and small algal cells occupy the surface waters using dissolved carbon dioxide and sunlight to produce organic matter. Their presence gives nutrient-rich regions a slight greenish cast when viewed from above, especially in belts of upwelling or near productive continental margins. Mixed among them are acritarchs, a broad group of organic walled microfossils that represent resting stages or cysts of various planktonic organisms. These tiny spheres and spiny forms are only fractions of a millimeter across, yet they are abundant in many Paleozoic surface waters. When they die, or when cysts are shed, their walls sink slowly, adding fine organic particles to the sediment rain that falls through the water column. In some parts of the ocean, silica-secreting plankton, such as radiolarians, appear and gradually diversify. These organisms build delicate skeletons from dissolved silica, producing intricate lattice-like shells that enclose their soft inner parts. When they die, their empty skeletons descend, surviving partially or fully, to reach the seafloor, where they accumulate as siliceous ooze in regions where dissolution is limited and supply is high. Elsewhere, dissolution in the water column or at the sediment surface breaks down many of these skeletal remains, returning silica to solution and limiting the thickness of siliceous deposits. Calcareous microplankton also contribute to the fine debris in late Paleozoic seas. Some algae and small planktonic organisms secrete calcium carbonate plates or tiny shells that fall apart into grains when they die. These grains mix with larger skeletal fragments from invertebrates and form part of the carbonate mud that blankets many shelves and the tops of seamounts and platforms. In shallow, warm settings, the constant production and breakdown of such microscopic and near-microscopic bodies helps keep the water column saturated with carbonate particles, which remain suspended during storms and then settle in quiet periods as uniform fine-grained layers. Animal-derived microstructures also play a role. Conodont elements, which are tiny tooth-like phosphatic structures from eel-like vertebrates that live in the Paleozoic seas, are scattered through marine sediments. Each element is only a few millimeters long, but they are produced in vast numbers over time. As conodont animals die or shed their elements, those structures fall to the bottom and become mixed into lime muds, shales, and other deposits. Later, these resilient phosphatic pieces persist through burial and lithification, becoming common microfossils in Paleozoic rocks and retaining details of their original shape and, in some cases, microscopic internal structure. Graptolites, while often preserved at a scale visible to the naked eye, leave behind tiny fragments and carbon films that further enrich the fine organic component of sediments. Many graptolite colonies live in the open water attached to floating structures. When these colonies die and sink, their remains break apart and distribute carbon-rich material through the water column. On the seafloor, their flattened impressions become thin, dark markings within mudstones and shales, recording both the presence of the animals and the low-energy conditions under which their remains were buried. At the interface between water and sediment, microbial life continues to act at small scales. On shallow shelves, cyanobacteria and other microbes form films and mats on the seafloor wherever light and conditions allow. These mats trap fine sediment grains, stabilize surfaces against erosion, and can induce the precipitation of minerals. Over time, repeated cycles of growth, burial, and cementation create laminated structures in which thin layers of mineral material alternate with organic-rich laminae. In some environments, these layered features form recognizable mound-like structures, while in others they remain as subtle planar laminations that nonetheless carry clear signs of microbial influence. Within the upper centimeters of sediment bacteria and other microbes drive many of the redox reactions that control how elements are partitioned among mineral and dissolved phases. They oxidize or reduce iron, sulfur, carbon, and nitrogen species, producing gradients in pore water composition over very short distances. As a result, even slices of sediment only a few millimeters thick can show bands of different colors and mineral contents that reflect the depth and intensity of microbial activity at the time of deposition and early burial. The remains of microscopic organisms also help define the boundaries between oxygenated and oxygen-poor zones in the water column. In regions of high surface productivity, large numbers of plankton die and sink, forming a concentrated flux of organic matter. As this material is decomposed by microbes at depth, it consumes oxygen. If the supply of oxygen from above is limited by stratification or restricted circulation, midwater oxygen, minimum zones, or anoxic layers can develop. These zones are not visible as sharp lines, but as thick intervals in the water column where dissolved oxygen levels are low. Their presence influences which organisms can inhabit those depths and affects the preservation of microfossils in the sediments below. In low oxygen environments, delicate organic walled microfossils and fine carbonaceous material are more likely to escape complete decomposition and be preserved in black shales and other dark deposits. In better oxygenated settings, burrowing and feeding by benthic animals, rework the upper sediment and expose organic particles to more complete breakdown. Along coastal and shelf environments, microscopic remains from land also entered the marine system. Spores from early land plants are produced in large quantities and carried by wind and water into nearby seas. These spores are often robust with resistant outer walls that can withstand transport and burial. They become mixed with marine microfossils in coastal sediments, forming distinct assemblages that record both terrestrial and marine influences. In estuaries and nearshore bays where fresh and marine waters meet the microscopic content of the water, and sediments reflects a blend of sources: marine plankton, freshwater algae, spores, pollen, in later parts of the Paleozoic, and fine organic debris from land plants and soils. The cumulative effect of all these microscopic bodies and their fragments is to give Paleozoic seawater a characteristic suspended load and to infuse marine sediments with a rich record of tiny structures. In clear oligotrophic parts of the open ocean, low concentrations of plankton and fine particles keep the water transparent and deep blue, while in productive upwelling zones or near river mouths, higher concentrations of tiny cells and organic detritus increase turbidity and shift surface colors toward green or brown. At the seafloor, layers only a few millimeters thick can contain thousands to millions of individual microfossils, even though the sediments appear uniform to the unaided eye. Over time, as these layers are buried and turned into rock, the microscopic bodies they contain become important markers of age, environmental conditions, and water chemistry. But within the Paleozoic seas themselves, they function simply as pervasive fine-scale components of the living and non-living material that fills the water and settles quietly grain by grain and shell by shell across the wide floors of ancient ocean basins. On land during the Paleozoic, many of the most durable records of landscapes come not from large forms such as mountains and valleys, which are reshaped by later processes, but from small traces left in sediments by organisms, water, and chemical changes. These traces persist as fine marks of ancient surfaces, preserving how the ground is used and altered at particular moments within this era. Early in the Paleozoic, when continents are still largely bare of complex vegetation, microbial mats and simple invertebrates leave the first subtle signatures. On tidal flats and shallow floors that are periodically exposed, thin layers of microbes grow over mud and sand, binding grains into cohesive skins. When water levels fall, these skins dry and crack, forming polygonal patterns and curled flakes. Later floods bury them under fresh sediment, and with burial they become preserved as thin, crinkled laminae within sandstone and shale. On coasts and in shallow seas, early burrowing animals create networks of thin tubes in the upper sediment. Their movements mix grains and leave rows of back-filled tunnels, branching passages, and resting hollows. When later layers seal these surfaces, the burrow systems become trace fossils, recording the presence of organisms even when their bodies are not preserved. Some traces appear as simple horizontal tubes, while others form spiral or vertical structures that show how animals move between deeper layers and the surface. Ripple marks, mud cracks, raindrop impressions, and tool marks from objects dragged across the bottom by currents join these biological traces, creating surfaces that are densely patterned at the scale of centimeters or less. As life spreads onto land, new traces appear on subaerial surfaces. On floodplains, lake margins, and coastal flats, arthropods and early vertebrates leave footprints and trackways in moist sediment. Each footfall presses into the soft substrate, displacing grains and sometimes deforming underlying laminae. When the surface dries slightly and is then covered by a thin layer of fresh silt or sand, during the next flood, these impressions are preserved as natural molds and casts. Over time, surfaces with multiple overlapping trackways accumulate, showing the paths of numerous individuals. Some trackways are narrow and closely spaced, made by small invertebrates. Others are broader, with alternating impressions that record the gait of larger limb-bearing animals. The three-dimensional structure of these tracks, including rims of pushed-up sediment and shallow slips, preserves information about the consistency of the substrate and the direction of movement. Spores from early land plants are another pervasive microscopic trace. Produced in large numbers by bryophyte-like plants and later by vascular plants and trees, spores accumulate on soil surfaces in small depressions and in bodies of standing water. When these areas receive sediment, spores become part of the fine-grained layers that settle out. Their resistant outer walls allow them to survive burial and compaction, so vertical sequences of rock record changes in spore types and abundance through time. In some beds, spores are densely concentrated, creating dark organic rich bands. At larger scales, the remains of plant tissues and roots leave their own patterns. In soils under early forests, root traces penetrate downward from ancient land surfaces into underlying sediment and weathered rock. These root systems often appear as branching tubular structures filled with material different from the host sediment, because roots alter the chemistry of their surroundings and create pathways for later fluids. When the original organic material decays, the spaces may be filled with minerals that precipitate from groundwater, preserving the form of the root network. On old floodplain surfaces, fossilized tree stumps may remain in growth position, with root traces radiating outward from a central base. Their arrangement outlines the spacing and density of ancient stands of trees. In Carboniferous peatlands, layers of compressed plant material retain fine anatomical details. Even after peat begins to transform into coal, thin sections reveal the outlines of tissues and spores preserved as carbon-rich microstructures. On bedding plains, in coal and associated sediments, flattened logs, seeds and leaf fragments appear aligned with water flow or scattered in patterns that reflect how plant debris accumulates in swamps and channels. These patterns, though made of organic matter, function as sedimentary textures that describe how material moves through the late Paleozoic lowlands. In arid and semi-arid Permian interiors, fine surface textures also carry information. Wind-shaped sand grains leave cross-bedding in dunes with distinct lamination angles and grain size trends. On exposed mudflats and saline pans, polygonal networks of cracks form as the surface dries. Later floods or wind-blown dust fill these cracks, creating casts and veins of slightly different composition. Animal tracks in these environments are often crisp and shallow, sharply outlined against smooth backgrounds. Combined with raindrop pits, adhesion ripples, and tiny scour marks from short-lived flows of water, they document how dry landscapes experience episodic wetting. At high latitudes, glacial processes generate their own fine scale marks. Striations and grooves on bedrock surfaces record the direction of ice movement carved by stones embedded in the ice base. When glaciers retreat, These polished surfaces may be overlain by thin deposits of till containing scratched and faceted clasts. In lake sediments fed by meltwater, annual couplets of silt and clay form, where seasonal changes in runoff control the size of particles delivered to the basin. Each pair of layers is only a fraction of a millimeter to a few millimeters thick, but sequences of many thousands of such layers accumulate, documenting long intervals of time in a rhythmic pattern. Across all these settings, chemical traces accompany physical and biological ones. Thin coatings of iron oxides, small manganese nodules, subtle color bands tied to redox fronts, and the distribution of certain minerals reflect how fluids move through sediments and how microbial and inorganic reactions proceed. For example, the boundary between oxygenated and oxygen-poor conditions within sediments can produce sharp changes in color over distances of a few millimeters, with upper layers appearing reddish or brown and deeper layers turning gray or black. When these materials harden into rock, these contrasts remain visible as fine bands or patches. Together, these micro-scale traces form the innermost layer in the description of Paleozoic Earth. Above them lie more obvious features: forests, river swamps, dunes, glaciers, reefs, shelves, and open oceans under changing skies. At the smallest scales, however, it is footprints, burrows, root networks, spores, laminae, and chemical fronts that preserve the most detailed snapshots of how surfaces look and function at particular times and places, carrying the memory of environments that no longer exist on the surface today.